Hi, everybody. Thanks for joining me today for this pre-algebra course. Can everybody hear me all right? Just give me a thumbs up in the chat bar if you can. Just to let me know. Cool. Also, what you can do for me, which would be amazing. My name is Neil, and I'll be your teacher for this course. If you could write your name in the chat bar, that'd be really great, because I don't have a class list with me here. So it'd be great to know everybody's name so that I can ask you questions. Cool. Hello, Samson. Samson, hello, Brian. We got a lot to talk about today. So when we start talking about pre-algebra, the place that we start usually is talking about some rules for really basic algebra. We need to know how to add things, subtract things, multiply things together, and the rules that govern that. And you've all probably done that already with single numbers, but different things happen when we have larger strings of numbers added together. And so the first thing we're going to talk about is the idea of commutivity. And that's specifically applied to addition. So the first thing I'm going to talk about is the idea that addition is commutative. This word commutative. And I'm just going to fix my V there because sometimes my writing isn't the clearest. So just let me know if there's a word that you can't read when I'm writing out what I'm saying here. So addition is commutative. And what that means is we could take a string of numbers like 1 plus 2, and that's the same thing as saying 2 plus 1. That's all. That's all it's saying, is that we can change the order of numbers that we are adding together. And it doesn't matter how many numbers we have, we can change them all around. So this just has to do with the idea, you can remember this by what, the word commute means. It's like if you've heard people talk about their commute to work. Commute is just is moving. So we can move these numbers around. They're not stuck when we're adding. So specifically, addition is commutative. And the way, the book, the Art of Problem Solving book, demonstrates this, a proof for this is by using these diagrams, these boxes here. Let's say if we have 2 boxes and we add 3 boxes here, we can get, 2 and 3 boxes added together like that. Whereas if we decided to add 3 boxes plus 2 boxes the other way around, we're going to get 3 and 2 boxes. Now you might say these pictures look different, This one is a reflection. This one is a reflection of this one. It almost looks like it's been flipped upside down. But the point is that we have the same number of boxes. So this might seem obvious, but it's a way that they use pictures to sort of visualize why this is true. So it's not a real mathematical proof, but it's an intuitive proof using shapes. So they do this a bunch of times in this first chapter. So it's a helpful way to sort of intuitively see, yeah, if I add one thing to another, it's the same thing as adding the second thing to the first thing. So in general, just going to save my slide here. In general, this commutativity rule is just A plus B is equal to B plus A. So I like to write this out. Once we define a rule, you'll see this in math. We want to define it for all numbers. So it doesn't matter what A is or B is. This works for any numbers that we could possibly work with in math. So that's why they write A plus B is B plus A. We use this is using variables that can be any number. You'd say where A and B are any number. Cool. Hello. Thanks for joining.
Hello.
So the second principle I wanted to talk about today after commutativity is associativity. So just write that out. Addition. Addition is also associative. And what that means is we can group numbers together when we have a long string that are being added together. So we could say, if I had something like 2 plus 3 in brackets plus 4, this is equal to 2 plus 3 plus 4. So let's just see what's happened here. In the left side, these brackets, do people remember what the Pemdas, the order of operations for addition, subtraction, and multiplication? We should just go over that briefly. So Pemdas, I should have actually written it like Pemdas. So this is parentheses. That's another word for brackets. The curvy brackets is what we call parentheses. An actual bracket is the square bracket like that. And I'll use a mix of both, but sort of interchangeable, bracket and parentheses. This the E stands for exponent. M is for multiplication. D is for division. We have addition and subtraction. So this represents the order of operations that you need to carry out in order to add and subtract mathematical expressions here. So I should I didn't remind people, but or say this yet, but after I teach the course every week, I save the slides and I send them to you. So or I upload them to the Google Classroom. So all of these slides that I'm writing will be available to you if you want to go back and look at any of them. So you don't need to write out everything that I'm writing out. So I just wanted to put that out there. When I post the homework after every class, the slides will be in the link as well. Cool. So back to this this order of operations tells me that if I ever have anything in parentheses, that has to be what I compute first. So we do have parentheses here. So we have to look to those to see what we add together first. We don't have any exponents. We don't have any multiplication, division. So the next one would be addition. So that's all we're doing here is we're adding. But the associative law says that we can add these in any order we want. We can group them. We can first add the 2 plus 3 and then add the 4, or we can add the 3 and the 4 and then add the 2. It seems like a simple idea, but it becomes very important when we have large strings of numbers operating in mathematical expression, and we might want to add things in a different order in which we see them. So again, the book has a way of sort of illustrating this using boxes, like a box diagram. But in general, we can understand it in terms of math, in terms of algebra. We say that a plus b in brackets plus c is equal to a plus b plus c. Again, where a, b, and c are any number. So this is the associative property for math, for addition. So yeah, these are the two most important rules here that we're going to be using in the next couple of weeks. So again, it's commutative. You can change the order that we add numbers together in, and the associative property means we can group them and we can add certain ones together first. So we can look at, a couple examples of this. Why is this useful to know? We could say, what is the easiest way to compute, 472 plus 219 plus 28? If we were given this, again, this is simple for a lot of people to add these numbers in their head, but there's definitely a more straightforward way to add these numbers together. Two of them will be added together easier. If we look at Pemdas, like we just talked about, it tells me to do the parentheses first. So if I look at the parentheses and I say, well, 219 plus 28, I could add those together, but sometimes it's advantageous to see that two of the numbers will be added together maybe slightly easier. If we look at 472 and 28, we say, oh, well, that makes a perfect 500. So how does this tie into the commutivity and associativity that we just talked about? So by the commutative property, I could rewrite this as 472 plus 28 plus 219. That's just by the commutivity. So I've switched the order of these. And then by the associative property, I could say that this is equal to 472 plus 28, all in brackets, plus 219. I should actually be writing associative property, because these are properties. The book distinguishes between properties and laws. So these are commutative property and associative property. So this would have made it easier to say, now I have, okay, 500 plus 219, which we can easily compute in our head, 719. So one of the reasons why the book starts off showing this example is because it's always advantageous to look to see if there's if there's an easier way to do what you have to do, or to see patterns, to make addition easier, or subtraction easier. And lots of times it's not just about making it easier, but it'll help you solve a problem, maybe in a different way than you would have thought from the beginning. Okay. So if I asked you to compute 2 plus 12 plus So if I asked you to compute something like this, you could say, well, it's a long string of numbers. It's kind of a drag. But is there a way that we could make this easier? What would be the easiest way that we could compute this here? Anybody have any ideas? If you want to suggest something, you could write it in the chat bar, or you could raise your hand, or if you just want to, you can start your microphone and say a suggestion. We don't have that many people in the class, so how could we make this this string of numbers easier to add using the commutative and the associative principle? The fact that we can pick and choose which ones we add together first. What would be an easier way to do this in our heads?
Maybe like add like 2 with 8 and 12 with 18. No.
Sure. Yeah. What would that look like?
Actually, like 38 with 2.
Okay.
And then 12 with 28, 22 with 18, and 32 with 8, because then all the numbers, all of those, that will be 4 40s, which is 160.
Right. So let's look to see what that would be. So we got 2 plus 38. That's a good suggestion. And what I'm going to do is say, before we do that, before we start using brackets, I'm just going to say 2 plus 38 plus 12 plus 28 plus 22 plus 18 plus 32 plus 8. So what this is the commutative property. It's going to let me do that. It's going to let me change the order. And then the associative property the associative property tells me, okay, now I can add them together in this order, 2 at a time in brackets. So again, this is something we do in our heads most of the time, but I wanted to like really slow this down and say, these are the laws, these are the properties that allow us to do this. So you're absolutely right, Brian, that each of these additions will add to 40. So we've discovered a pattern, and We could even write this as 4 times 40. We haven't got there yet. 4 times 40, which is 160. So sometimes we might be given really long strings of numbers, like numbers from 1 to 1,000. So this is going to be really important to be able to do this, to establish a sort of pattern like this. Just going to save my slide here. Does anybody have any questions about this? Okay. So here's a problem from the book. Find the sum of the positive integers from 1 to 20. Find the sum of the positive integers from 1 to 20. So this is like saying 1 plus 2 plus 3 plus 4 dot 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 plus 20, all the way up to 20. What would be a fast way to do this using the commutative and associative principles? How could we speed this process up?
You make the numbers all add up to 20, like 1 plus 19, 2 plus 18.
Yeah. Yeah, so which ones are we're going to add, which ones are we going to combine together?
1 and 19, 2 and 18, 3 and 17, 4 and 16, 5 and 15, 6 and 14.
Okay.
7 and 13, and 8 and 12 and 9 and 11, and just leave, and then just add 10.
Yeah, and what is the last one?
10.
10. Yeah, 10 is sort of by itself though then. Because then we'd have 10 and 20 left over, right?
Yes.
So maybe let's try, that would work. That'd work. And if you could keep track of that stuff in your head, that's all right. Let's try, what if we said, well, what's 1 plus 20? And then 2 plus 19. Because we have an even number of integers, right? We have 1 all the way to 20. So it's 20 integers. So it'd be great if we could get 10 pairs that were all the same. Are these going to add up to the same? 3 plus 18. All of these additions add up to 21, right? What is the last pair in this string of numbers? If we're counting up 1 plus 20, 2 plus 19, 3 plus 18, what is the last pair that we're going to get to?
10 and 11.
10 and 11, exactly. So we're going to get another, and that's 21. So we can rewrite this as 10 pairs of 21. So 10 times 21, which is equal to 210. So again, this isn't that many numbers, but I could ask you to add the integers from 1 to 1,000. And we would need to establish some sort of pattern to do that, because we don't want to sit there with our calculator and add every integer together from 1 to 1,000. It would take all day. Sorry, I didn't get your name. Is it Gia?
No. It's actually my mom's name, but my real name is Shayla.
Shayla. How do you spell Shayla?
Shayla.
Hayla. Shayla, cool. Nice to meet you. Cool. Okay. So that's for addition. Simple idea. The idea that we can change the order that we add things together in. That's all. I'm going to talk about multiplication now. Multiplication is also commutative and associative. So we can take these same ideas and say they apply to multiplication. So the first one, commutivity, commutative, means that 2 times 3, well, I'm going to write a multiplication sign here. 2 times 3 is equal to 3 times 2. It means we can multiply them in any order we want. And, you know, the way that they show that in the book with these diagrams, they say we could have either 2 times 3 blocks, and that would give us 2 rows of 3 here. Added together would give us 6 blocks. Or we could have 3 rows of 2 blocks. And that's going to give us this configuration here, which looks different, but it looks like it's been rotated, but it's still the same number of blocks. So this is one way the book sort of shows this to be true. Anyway, this may be too simple for people, but in general, we say that A times B is equal to B times A for the commutative property of multiplication. So when I don't use a multiplication sign between two things, it means they're multiplied together. Have people seen that before? We could say that, yeah, that's an aside. I could say that, you know, A times B is equal to A times B. Sometimes we use a dot, which is equal to AB. Those are all different ways of writing multiply. Is that new for people, or have people seen that before? These different ways.
I've seen that before.
Okay, good.
I've seen that before.
Okay, cool. So I'm going to kind of switch between them depending, because when we start using x as a variable, it's going to get confusing to write the multiplication sign out. It's going to look like an x. So that's why we start using the usually the dot or nothing at all between two variables. Okay. Save my slide here. So the associative property for multiplication looks like 2 times 3 times 4 would be equivalent to 2 times 3 times 4. So it's the same thing like we did for addition. It doesn't matter what order we multiply them together. If everything is being multiplied together, we can pick and choose which ones we multiply first. Okay. So in general, with variables, we write just the same thing. A, B times C is equal to A times B times C. So there I didn't use any multiplication signs. It means the same thing. So that is our associative property. Again, this might be a review for people, and I'm sorry if it's moving slowly at first, but it's important that we establish these rules before we move on. So if I were to ask you, you know, is there an easy way to compute something like 25 times 125 times 4 times 6 times 8? If we were to have this long string of numbers, maybe it's not that long, and we were told to multiply these together, could we use the commutative and the associative properties to simplify this? To simplify the order in which we do this. Oh, there's some pairs here that might be easier to multiply together. Well, what's one pair that would be easy? Instead of multiplying 25 by 125, what could I multiply 25 by to get a nice round number?
25 times 6 equals to 150.
Sure, we could do 25 times 6. So that would be 150. What would be another pairing that would be good? If we
125 times 8 is 1,000.
125 times 8 is 1,000, exactly. So for that one, we would have 4 left over. So we could say, 4 times 150 might be easier than, we could say 400, that'd be 600. So if we said 150 times 4 times 1,000, then that's going to equal 600 times 1,000. And multiplying by 1,000 is easy. We just add the 3 zeros. So it's the way that the book pairs them up, they said, well, you could say, or 25 times 4, because that makes 100, and 125 times 8, you got that one. And then they do times 6. They do it slightly differently, so that they get 100 times 1,000 times 6, but it equals the same thing. The point is they're always looking for numbers that will multiply together to give nice round numbers like 1,000 or 1,000,000, something like that. So there's some exercises that I'll post afterwards that has you practicing these rules here. So we already talked about order of operations a little bit. That's our Pemdas. That's what they call the, that's PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. So just before we move on, I would just like to say, okay, is 5 plus 6 times 7, is that equal to 5 plus 6 times 7? Do our commutivity and associativity principles apply here? Samson says no. Yeah. Is it Yukai? Is that your name? Sorry, I didn't get your name either before when we started.
My name is Yukai.
Yukai, cool. Yeah, so Yukai says no as well. So this is a mix of both. addition and multiplication. So using the commutativity and associative principles, it doesn't work here. We can't just change the order that we do this in. This would be the associative with the brackets, right? Changing where the brackets are. So and changing them to here, that would be the associative principle, and that does not work when you have a mix of multiplication and addition. So we have to be very careful. If we were to compute the left side, we're going to get 11 here times 7, and here we're going to get 42. So this is going to give us 77 is equal to 47, which is not true, obviously. So although we've learned these commutative and associative principles, we have to be very careful that we're not using them in conjunction with multiplication and addition at the same time. The next important thing that I want to go over, the next property, is the distributive property. Just gonna, before I go on, I have to keep remembering to save my slides because sometimes the program crashes here and I don't want to lose them. Okay, the distributive property. Has anybody heard of the distributive property before?
I have heard of it.
I have.
What is it? What is it? Does anybody, can you explain it in words? It's okay if you can't. No, it's good that you've heard of it. The distributive property is when you have something like A and it's multiplying B plus C. Does anybody know how we do this multiplication? How we would multiply these together. So this is the situation, a specific example would be if you had something like 2 times 3 plus 4. The distributive property says we distribute, because distributing means, to allocate, around to everything. We distribute amongst a group of things. We distribute the A to the B and the C. So we end up with two products, A times B and A times C. So there's a lot of language that they use. Sometimes we call this expanding the brackets. So this is like, I'm going to write that because that's something I'm going to say a lot, expanding the brackets. Expanding the brackets. Multiplying A into B plus C. You could say I'm multiplying A to B plus C. I'm distributing A into B plus C. We can say all of these things and we mean the same thing. It just means I'm multiplying A into the brackets B plus C. And that's the distributive property. It says A gets multiplied by everything that's in these brackets. So if you had 2 times 3 plus 4, we could write this as two products. We could say this is 2 times 3 plus 2 times 4. So 2 times 3 plus 2 times 4. Okay. And we could say, okay, well, 2 times 3 is 6, 2 times 4 is 8, which is 14. We could have also just followed the rules of Pemdas and said 2 times 3 plus 4 is equal to 2 times 7. because PEMDAS tells me to do the parentheses first, right? If you remember PEMDAS, PEMDAS is saying, oh, well, do what's in the brackets first, and we're going to get 14. So it's the same answer, but in certain instances, it's going to be more important to do the distributive property way, because we're not going to have numbers, we're going to have variables. So I'll write out an example where we have variables. It might say, 2x times 3y minus z. They might say, well, how do I simplify something like this? I can't just add 3y plus z minus z together. I can't do that subtraction because z and y, they're not like terms. It's not the same variables. It's not like saying I have, 3y minus z is like saying I've got 3 bananas and I want to take away an apple. You can't take away an apple from 3 bananas. They're different things. So the way that we would simplify this with the distributive property would be to say, well, this is 2x times 3y minus 2x times z. We would have distributed. And then we could do the multiplication here. Does anybody know what 2x plus 2x times 3y would be? We did that multiplication.
6y?
It's going to be equal to 6 xy. We still have to have that x variable in there. And then we're going to get negative 2xz. So this is what would be the simplified form of this if they asked us to expand. Sometimes they'll say expand. That's the only directive they give you. Sometimes they say compute or expand. So I'm just trying to go over the language here that we'll be using when we talk about algebra and math in general. So the distributive property, I'm just going to write it in general. Just says that a times b plus c is equal to ab plus ac. And we can change the order that we write it in by the commutative and say that this is equal to b plus c times a. We could say that as well. So it doesn't matter because multiplication follows the commutative property. So the distributive property is just a way that we do multiplication when we have brackets. Okay. Okay, so here's a question from the book. They say, compute 51 times 9 plus 51 times 31. Is there a way that we can use the distributive property to make this computation easier? If we remember the form of our distributive property, that's just a times b plus c is equal to ab plus ac. How could we use this idea to simplify this? Instead of just using the regular Pemdas method, where Pemdas says, well, oh, I think someone has their microphone on. There you go. So Pemdas tells me that I have to do multiplication first, right? Multiplication before I do addition. But let's think about the distributive property down here and say, how could we use this form to simplify this? Does anybody have any ideas? We have 4 terms. But 2 of them are the same. How could I use what I have here, where I have 4 terms, to rewrite this in a way that might be easier to compute?
51 times 40.
Okay, cool. So in order to get 40, you would have had to, how would we rewrite that? How would we rewrite this line using distributive property then? You want to say 51 times 40, but how did you get there? What did you rearrange?
31 and 9.
31 and 9. So you wrote this out then as 51 times 9 plus 31, right?
Yes.
So does everybody see that that was like the reverse of the distributive property? We had the right side essentially. We had this, and we're writing it like this. Does everybody see that? Because that's important. We can go backwards with the distributive property. So you're absolutely right that this is 40. And 40 is a lot easier to multiply by 51 essentially, but 51 is still not a great number. So you know what I would do? Or they do this in the book. We could say this is equal to 50 plus 1 times 40. And then distribute the 40 again. We could say 50 times 40 plus 1 times 40. And these numbers are much easier to multiply. 2,000 and 1 times 40 is 40. So again, this may not seem like such a big deal if it's, you know, a small string of numbers like this, but it's going to be a lot more complicated when we have large strings of numbers. But it's always advantageous for you to look for patterns like this. If you're writing a math competition, or you know, a math test even at school that your teacher would give you, lots of times math teachers give you questions that can be solved easier if you recognize a pattern. So math is all about recognizing patterns. Okay. So this is actually what we did here. We factored out, we did the opposite of distribute in this question. We factored which is the opposite of distribute. We factored out 51. We factored out 51 from both of these. So we'll see more examples of that in a second. Or maybe I could just write another example of that. Just going to save my slides here. So if you had something like like 25x y minus 20x, we could do the opposite of the distributive property and factor this. What could we factor out? What do both terms, these are terms, these 2 terms, what are the things that both terms share? What are some factors Factors can be numbers or variables. What factors do these terms share? Let's think about the numbers, 25 and 20. Are there anything that, any numbers that divide evenly into both of those numbers?
5.
5, they both divide by 5. So we could say, I'm going to write 5 out front, and then say 5xy minus 4x. So we would have factored this out. Does that make sense? I factored out a factor of 5. We could also take the x out, right? X is a variable that they both share. So I could write x and take this x out. I'm just going to rewrite this as 5y minus 4. So this is the opposite of the distributive property. This is factoring. We factored out a factor of 5 and an x. Okay. So I just thought part of that last example was, using the distributive property, but it's using it backwards. It's factoring. It's not distributing. We're doing the opposite. So sometimes you might be asked to factor this expression. That's what the question would be. Okay. Just going to get rid of some of these slides here. Okay. How can we prove that A plus B times C is equal to A plus B times A plus C? How could we prove if this was true or not? Has anybody been asked to prove a mathematical statement before in general? Well, first of all, one thing that you should think of if you're ever asked to prove a mathematical statement is, do you think it's true? Do you think this is true? How would you
Yes.
how would you decide if this was true? What makes you say yes? Or maybe does anybody else say no?
I think it's true.
You think it's true? Okay. Why do you think it's true?
Because when you separate the B and C, like A times B and A times C equals to A plus B and A plus C.
Okay. So you're doing like the distributive property, right?
Yeah.
But we can't really the distributive property.
Not like it, I think it's incorrect because I tried it out and it didn't work.
Aha. So one way is to try it out. You mean try it out with real numbers?
Yeah.
sorry, I forget who was speaking. Was it Brian who was just speaking?
Yes.
Yeah, did you say you tried it out? Did you try it out with actual numbers? Like, did you say?
Yeah,
real?
I turned A into a number and B into a number and C into a number.
Okay, so we could say, what did you let A, B, and C equal?
I let A equal 2, B equal 4, and C equal 3.
Okay, let's try it out. So we get 2 plus 4 times 3 is equal to A plus B would be 2 plus 4 times A plus C would be 2 plus 3. So the left side here from Pemdas, we would have to do the parentheses first. So that would be 12 plus, so 2 plus 12. And this would be 2 plus 4 is 6 times 2 plus 3 is 5. So 14. It doesn't look like it's equal to 30. So this is not true. So you've proven then that this is not true. I think someone has their microphone on there. Okay, cool. So it's really easy to prove a lot of times that something is not true, because all you have to do is supply one case where it's not true. So you can substitute in some values. That's the easiest thing to do when you're confronted with a proof that you're not sure is true or not. Shayla, the distributive property only works when we're using multiplication. So remember, the distributive property said that this is true. This is the distributive property. But what we have up there is A plus B times C. And they're saying, does that equal A plus B times A plus C? So these are two very different statements. We have to just be very careful what the operation is that they're asking us to compute. That we have do we have a plus in there, or do we have nothing? Do we have a multiplication? Because these are very different. So keep in mind that this is the true one, and the one below is untrue. And one of the easiest ways we can prove that something is not true is just by subbing in some values. Now, if you had found, Brian, if you had found that that was true, that worked for those numbers, the A, B, and C that you plugged in, it wouldn't necessarily mean it was true for all numbers. That's the funny thing about proofs, is that just because something works for some numbers, some specific numbers that you choose, it doesn't mean it's true for all numbers. So proofs are a lot harder to do when you're trying to prove something is correct for all numbers than it is to get one example and say that it doesn't work. We'll see some more proofs later on in the course. Okay, I want to stay on the distributive property for a second. So how can we use the distributive property to multiply A plus B times X plus Y? Has anybody ever multiplied something like this before? Where we have two terms Two variables added together in each bracket. These are called binomials, actually. We know the distributive property says that A times B plus C is equal to AB plus AC, because we get this distribution happening. But how does this work if we have a whole bracket here that we're distributing? What could we write that would be true? Any ideas? What would the distributive property allow us to write? If we wanted to expand these brackets. I'll give you a hint. We can, because this is a multiplication, this is still multiplying this times this. Can we use the distributive property, this stuff here, and just say instead of A, we have A plus B? Can we distribute this whole bracket into this, into there? Would that work? Could I say A plus B times X and A plus B times Y? So I could say A plus B times X plus A plus B times Y. Does that follow the rule of the distributive property? I think so. It does. Because we're just taking A plus B as a package and saying, well, I'm going to distribute that A plus B into the next bracket, into each term of the next bracket. And now we just have another distributive property where we can distribute the X into this bracket, into each term there, and the Y into this bracket here. What would I write as my final line here if I distribute the X in? What would the final line here be once the X and the Y are distributed in? What would I write once I distribute this X and Y in? Anybody have any ideas?
XA plus XB plus YA plus YB.
Right, exactly. So we're going to end up with 4 terms. Cool. The regular distributive property, as we wrote up here, we just end up with 2 terms because we're distributing one variable into a bracket with 2. But here we have, 2 variables multiplying 2 variables. So we're going to end up with 4 terms at the end. But we didn't do anything different than just apply the distributive property, but we applied it twice. So that's an example that I think is important. That's going to come up later in several weeks' time. We're going to revisit this, but it's just an extension of the distributive property. You can always take something and multiply it into a bracket. You know, it doesn't matter how many things we have. You could say I have 2x times, you know, 3x plus, well, let's just do 3y plus 7z plus, you know, 2a. You know, we can have any number of things in a bracket here. And we go to distribute this. If I'm going to use the distributive property, that means I've got to distribute this 2x into everything that's in there. So multiplying this out, we're going to get 2x times 3y plus 2x times 7z plus 2x times 2a. So you can see it gets quite large the more terms we have in here, multiplying all these things out. And just like we did before in that last example, we can multiply the number parts together and write the variables side by side. So 2 times 3 is going to give us 6, and then we write the variables there. And 2 times 7 is going to give us 14, and then we write the variables xz. And 2 times 2 is going to be 4, and we can write the variables x and a. Cool. So another really important idea that you're probably all familiar with is negation. Negation, the idea that a number is negative, the negative version of a number. So the negation of x is negative x. And another way we can think about it is it's the number that we have to add to x to get 0. That's one definition of negation. So we could say x plus negative x is going to be x minus x, which is 0. So for this, we can think about the number line. So if we think about the number line, 1, 2, 3, 4, 5, 6. So we can have 1, 2, 3, 4, 5, 6 in the positive direction. But we can also go in the negative direction, -1, -2, -3, -4, and so on, all the way to negative infinity down there. This is an important idea to think about the idea of negation. So if we wanted the negation of 4, that's going to be -4. And if we added 4 to -4, we're going to get 0. That's going to bring us back to 0 there. So we could say 4 plus -4 is going to equal 4 minus 4, which is 0. What happens when we get the negation of a negation? If I have negative times negative x, what does that give me? Does anybody know?
Positive x.
Positive x. Yeah, a negation of a negation gives us positive again. So that's the old thing, like a negative number times a negative number is going to give us a positive number. So if I had something like, you know, -2 times -3, that's going to give me +6. And that is the way that multiplication works with negation. Okay. Negative numbers are going to come up all over the place here. So one of the ways that the book shows that this is true, show that -2 times -3 is equal to 2 times 3. They say, okay, well, the left side is equal to, okay, -2 times -3, which we could say, I'm going to separate this into -1 times 2 and into -1 times 3. So I'm factoring these negatives out. That's this word again, factoring. I'm factoring out a -1 from both -2 and -3. And the commutative property of multiplication says that I can write these in any order that I want. So if I can write these in any order that I want, I can multiply the -1 times -1. And we know that -1 times -1 is going to be +1. I think it was Brian that told us that. So basically, it cancels out the negative, and we're just left with 2 times 3, which is the right side. So that would be a sufficient proof to show that the left side is equal to the right side. Does anybody have any questions about that? People, you can stop me at any time, and we can talk about something more in depth. It's nice that we have an hour and a half together every time we meet, because an hour sometimes doesn't feel like enough time. Negation always, the distributive property also works with negation. So with negation, if you have -x plus y, and we wanted to expand these brackets, we could rewrite this having, you know, the idea that there's a negative out front of this bracket means this is like multiplying these brackets by -1. This is like saying I have a -1 out here and I'm multiplying it by x plus y. And if we think about it like that, we can say, well, I'm going to use the distributive property to distribute this -1 inside there. What am I going to get if I distribute this -1 inside? What are we going to get left with? Does someone want to do that multiplication?
-1.
What am I going to get left with if I
-x times -y.
-1? Well, it's going to be -x plus -y, really. Let's just see why this is the case. Let's just go back a second and say, okay, if I have -1 times x, and then we're going to add -1 times y. but I want to get rid of some of these brackets. I don't want to have to write all of these brackets all the time. So negative 1 times x, you're right, is negative x. And then we have negative 1 times y. So we're adding negative y, because negative 1 times y is negative y. But then we don't have to write these brackets around the negative y. We can just write this as negative x minus y. Why can we write it like that? Because we had plus negative y. How come we can write it as just negative y? If we have a plus outside of a negative, it's like that.
It's like a negative because like plus a negation is a positive. I mean a negative.
Well, yeah, if we have if we are multiplying, like having a positive outside of a bracket, that's like saying I have plus 1 multiplying negative 1. A positive times a negative, which is going to be negative 1. So lots of times we're going to get a sign that's outside of a bracket, and we just multiply the signs together to get the resultant sign. So I'm actually going to multiply these signs. Together to get the resultant sign. Because we don't want to have to write all these extra brackets if we don't need to. Saying plus negative y is a lot more tedious than writing minus y. So if we had an example, you know, like 2 plus negative 3, we could say, well, that's the same thing as writing 2 minus 3, which is negative 1, as an example. So lots of times I'm using variables as, you know, to demonstrate these things so that we know that they work for any numbers. But it's always good to do an example with real numbers. So let's think about this for a second. I want to tally up all of our ideas about negation before we move on from that. So if we go back, if we just think about negation for a sec, we're going to have a lot of different possibilities. We're going to have like a positive number times a negative number, a negative number times a negative number, a negative number times a positive number. Positive times positive is easy. Positive times a positive is always going to give us a positive. Negative times a positive, we saw, is going to give us a negative number. Negative times a negative, we saw, is also going to give us a positive. And a positive times a negative is going to give us a negative. So anytime you have a multiplication of numbers that are positive and negative, we have to count the number of negatives we have. If we had, say, you know, negative 1 times negative 1 times negative 1, are we going to end up with a positive number or a negative number? What is the resultant product going to be?
Negative.
If we're going to end up with a negative, so how could we show this? Well, we know we have these two first, so we could say this is going to be a positive 1, because a negative 1 times a negative 1 is positive. And then we have the remaining negative 1 there. And then a positive 1 times a negative 1 we know is going to be a negative 1. You know, so we could say negative 1 times 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 negative 1. How can we use this rule to generalize? We don't have to do this multiplication every single time, right? Could we just count the number of negative 1s? What is this product going to be?
A positive?
Yes.
Because negative 1 times negative 1 is positive, and then negative 1 times negative 1 is positive, and negative 1 times negative 1 is positive, and positives times positive is a positive, which
Exactly. Right. So in other words, what could we say in general then is a rule if we're multiplying lots of numbers together with positives and negatives? What could we say? How do we know what the product is going to be, or the sign of the product, based on how many negatives we have?
It doesn't.
Yeah, go ahead.
We could just do 6.
if there was a even number of negatives, then that will be a positive. If there would be an odd number of negative numbers, then that will be a negative.
Right. So we just have to pay attention to whether there's an even or an odd number of negatives that we're multiplying together. So, so the product of an odd number of negatives equals negative, and the product of an even number of negatives is going to be positive. So we'll work more on that when we get to exponents. Just looking to see how much time we have left here. Sorry. Okay. 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 So just in the few minutes we have left here, let's try to do some examples here. If we have 11 minus 13, what will that simplify down to?
That will be 11 plus
13.
11 plus 13, right? Because we distributed this negative into there, a negative times a negative.
24.
Right. Which we can add together as 24. What about if I had negative 11 minus 13? What is negative 11 minus 13?
Negative 24.
It's going to be negative 24. Does everybody see why it's negative 24?
Yes.
We could think about the number line here. If we start out, say this is like, 0, 1, 2, 3. So this is our number line, negative 1, negative 2. When we're adding and subtracting, and we're starting out with negative 11, we can visualize that by saying, okay, I'm here on the number line at negative 11, and I want to subtract another 13. We're going to be moving to the left. We're going to be going more negative. Another way to think about this, though, is to say, I'm going to write this as negative 11 plus 13 by using the distributive property, like we used before, to factor out the negative. And then say, well, we already know that 11 plus 13 is 24. So that would give us negative 24 when we multiply the negative back in. Does everybody see the trick I used there? I factored out a negative. Factor a negative from both terms. It's just another way to see it using the distributive property. In almost all the questions that we do together, there's going to be more than one way of solving them. So it's partly part of my job is to show you different ways of understanding the same problems. Because you might be confronted with a situation one day where it might be helpful to think of a different way of doing it. What about negative 13? Negative 13 minus 11. What does that simplify down to?
Negative 12. I mean negative
Sorry, did you say
2.
negative 12?
Negative 2.
Negative 2. Negative 2, right. We could say this is equal to negative. We could simplify what's in the parentheses first. So 13 minus 11 is 2. And then obviously multiplying the negative in, we get negative 2. Or we could say, I'm going to distribute this negative in, negative 13 plus 11. So I'm starting 13, the number line, I'm adding 11, so I go more positive by 2 units. You can think about it both ways. So I'll give you lots of practice questions to practice these principles. So we have the commutative property, we have the associative property, and we have both of those for multiplication and adding, and we also have the distributive property that we talked about today. And negation is another important thing that we talked about today. So those 4 ideas, I'm going to post some questions now in the Google Classroom, and there'll be lots of examples for you to work through in the textbook. So the textbook that we're working from, The Art of Problem Solving, if you don't already have a PDF copy of that, you can reach out to Fiona who's organizing this course, and she will give you a link to a PDF version of this textbook, because I'm going to be assigning practice problems for you to work on out of this textbook. And I'm also going to be posting the solutions, so you can follow along each week with the questions. I tend to give a lot of questions for you to practice, and everybody has different amount of time to be able to spend working on these questions. I don't expect everybody to do every single, up to you, and how much you want to, how deep you want to go with this textbook. But there's always really challenging questions at the end of the chapter that I would really encourage you to try, because it's going to build your math skills, and it's going to help you not only in your in your day-to-day classes at school, but it's going to have competition. Math is all about collecting skills, sort of tricks. You're really just building the tricks, and the more you know, the more situations that you can understand. Thanks everybody for joining me today. I look forward to the rest of our sessions together, and keep your eye on the Google Classroom. I'm going to post some questions in the next 5 minutes here for you to try before next week. Are there any questions before we go?